at continuity. A function is called continuous if the curve of that function can be drawn without lifting the pen off the page. Example of a continuous function, it will be a parabola. That's one example. So let's draw it. I could draw the parabola without lifting the pen off the page. Pretty easy. Right? Like that. Yeah? I could draw without lifting the pen off the page. That's called continuous. That's one way of looking at it. Continuous is it can draw the graph without lifting the pen off the page. Now let's look at the definition offered by the textbook, which is an informal definition. A function fx is called continuous at x equal to a if the graph of fx can be drawn through that point without lifting the pencil off the page. If there's a break in the curve, we say there is a discontinuity at x equal to a. Now let's look at these questions. So we're going to look at some example of a discontinuous graph. So let's look at the first one. A function has a discontinuity at x equal to 2 and is continuous everywhere else. So can you see there's a break? So it's discontinuous if, for example, there is an asymptote. Yeah? Okay. So that means when you try to draw this graph, I have to lift the pen off the pencil before I go on to this part. Does it make sense? I have to lift my pen off the pencil. It's impossible to draw this graph without lifting your pen off the page. And the same thing with this. I have to draw this, have to lift my pen off the page before I draw the next part. They're disconnected. So the function has a discontinuity, in this case, at 1, and it's continuous everywhere else. All right, now we know what continuous and discontinuity mean, and we'll see example of that. Maybe in this case, like the hyperbola, right, 1 over x, that's discontinuous, right? We've seen many examples, but we probably haven't used this language to describe them yet. Now we are, right? Okay, let's move on to the next page. Okay, now we're going to look at piecewise defined functions. Oh, what's that? You probably have seen that before with the absolute value, because absolute value graph is an example of piecewise defined function. So what does that mean? A piecewise defined function has different definitions in different parts of its domain. For example, so let's look at this. So you could join 2 different graphs together. So it can be very flexible. F of x is x squared when x is less than 0. Bang. And when x is positive, we get the straight line. Bang. That's how simple it is. We join 2 pieces of 2 different graphs together. I mean, that's one very simple example. There's some harder ones, but you just have to follow what it means. It's called piecewise defined. And some textbooks call it piecemeal function. If you look up the website, you will see in some other textbook, they say piecemeal, piecewise. Okay, all right. Okay, the 2 pieces of this graph are a parabola and a line, but we need to find out whether these 2 parts join up or leave a gap. In this case, it's continuous. The most obvious way to construct is to construct 2 tables of values, one for each line of the function's definition. We have already met piecewise function in chapter 4. Chapter 4, piecewise defined. Okay, cool, like that. So that means, if you remember the definition of absolute value of x is x when x is positive, negative x when x is negative. As we've seen here, there are 2 graphs joined together. That's called the absolute value graph. It's like a special case of piecewise defined function. Okay, cool. So we can really make up new formulas. So you see there's parabolas, there's straight line graph, there's also things, but we can even combine things together. It's like Transformers. If you watch small episode of Transformers, different robots combined together become even super robot. Yeah, it's really fun. Yeah. But anyway, let's move on. Example 36. All right, 4 minus x squared. Okay, now we have a hard example. Do they join together? Maybe, maybe not. So what's the one way to find out is to draw them, right? Actually, what was the strategy offered? Yeah, we'll have to do table values or whatever. So we're going to do table of values. So for this one, on the left of x is 0, so we're going to substitute these numbers. -2 is 0, -1 is 3, 0 is 4, right? We'll see whether these two tables join. And on the other hand, as this part, 4 plus x squared, oh, that's meant to be a square, I forgot. Okay, so we're going to substitute 0, which is 4, 1, which is 5, 2 is 8. That's pretty cool. Now we're going to draw the graph. Let's draw the graph. So 4 minus x squared. So on the left of 0, we have 4. Actually, we'll put 4 here, and then we'll have 3, and then it just become like that, right? This is y equal to 4 minus x squared. And on the other hand, if I draw this one, 4 plus x squared goes like this. So they do join together. We'll sketch the graph. And the question is, what's the domain range? Well, once you sketch the graph, actually, sorry. Oh, it was meant to be x because I do copy and paste. Sorry. Actually, it doesn't matter. I meant to do xc. Oh, okay. Okay. Sorry. Okay, it meant to be a straight line because in the textbook they did a straight line. But anyway, that's good. Now you can look at the textbook for a different example. Okay, domain and range. Anyone want to have a try? Anyone want to try domain? Anyone? Yes, Alex? All real x. And the other Alex? Yes, thank you, all real y. All right, thank you. Well done. So it's pretty basic. We'll start with simple example and then move on to some harder ones. But they're not that hard. It's the same concept, just different graphs. So as you can see, mathematician can be very boring. We always talk about the same thing. Sketch the graph, what's the domain range? We always ask the same question. So do you think, if you someone study maths, you think this guy's so boring? Because he always say the same thing. Yeah, but anyway. On different matters, we say the same thing. So this guy's so boring. But anyway, we'll move on. So we got this another piece. So it doesn't have to be 2 functions. Could be 3 functions combined. Could be even more. But I think more extreme cases, you see exam papers will just have a maximum of 3. I don't think I've seen one will have 4. Oh, they could ask for 4, but I rarely see 4. I think 3 is the maximum usually. Okay, establish whether the graph is continuous at x equal to 1. Okay. Well, that's a hard question. Well, so what do I do? Try to check. Well, to check it, we just substitute 1 into all 3 places, right? So we substitute 1, even though it's not defined 1, we just want to check whether they join, right? Substitute 1, you get 2 to the power 1, you get 2. That's already 1. And that's 1, you get 1 square, you get, oh, unfortunately, that looks like they don't join. They don't join. In this case, we expect discontinuity. They don't join, right? Okay, so we're going to establish whether, so we say, now how do I explain that? So you don't have to write an essay about it. All you have to say is, when x is 1, 2 to the power x equal to, that's the working from the textbook, by the way. And when x, you just have to make it clear in the exam. Why is it continuous? Why is it not continuous? If it's clear, if it's negligible, we give you the marks. So obviously, so you say, because they don't match, you say hence the function. So you need to show this similar working out in the exam and in your homework. Again, you should have a habit of showing working. When you do show working, it will be so easy. You don't even know you're doing showing working. It's part of what you do. Okay, hence the function is not continuous at x equal to 1. Now, the graph will be very clear. Let's draw the graph. So on the left, it is an exponential function. Hopefully, you remember what it looks like. So 1, and then 1, it becomes 2. But it is going to be an open circle like that, right? Because it stops. How do I know that? X less than 1 is going to be an open circle. On the other hand, you get parabola. So if I draw it with a magic pen, this won't work. So you get a parabola in a different color, green, right? So you normally just draw this, right? But you start drawing when x is more than 1 from this point onwards. sense? Just from this point. So that's like a parabola, but only valid when x is more than 1. This is valid when x is less than 1. And how about the middle bit? X equal to 1 is 1. Well, it's just a point, right? Actually, that's 1. Yeah. Actually, that's only valid at x more than 1 without the equal. And that's when x is 1. That's y equal to 1 when x equal to 1. So be very, again, there are subtle stuff, subtle details. All right, we're going to get someone else to answer the next question. Domain, Samuel, that one. Yeah. Oreo X, can you do the range as well? Yes. Now, oh, they didn't join, but you expect to see a y, and I mean, you see two different y values. So in that case, we call that function one to many. Would it be one to many? No, one to many, right? Yes, one to many. One to many, because many, yeah, one to many function. All right, be careful with zero. Don't write zero like this, look like a 6. I just marked the year 7 test, and some of the zero look like a 6. It's just confusing. Make sure you write your numbers clearly. Oh, by the way, app break, it's a really, based on, let's move on, sorry, okay. Yep. All right, let's move on. Okay, so let's have a discussion about it. Where x equal to 1, the value of fx is 1, so the endpoint is 1, 1, right? On the left of the right-hand side of the piece is included in the graph as indicated by the closed circle. But the endpoint 1, 2 on the left piece is the open circle. It's not included in the graph as indicated by the open circle there. So you have to show these features on the graph. And that's summarized here. A closed circle marks endpoint that is included in the graph. Open circle means not included in the graph. An arrow marks a curve that continues forever. So that's why it goes on forever. Arrow. Whereas the application of calculus, we do not have arrows because in real life, I mean, like that one here. Which one? See, there's one graph. This one we got no arrow for a reason because it starts here, finish there. No arrows. Hopefully that makes sense. So again, depends on the context. You got to really think and follow your notes in the correct direction. I've got one more page, that's it. Okay, functions in which numerator and denominator have the same zero. A graph has discontinuities if it has, hello, if it has variables in the denominator. To find the discontinuities, all we have to do is to solve the denominator equal to 0. For example, find the x values for which the function is discontinuous. Find also the zeros of that function. Okay, well, discontinuities is when the denominator equal to 0. So you can work out discontinuities on the domain without drawing the graph. So you write equal to 0, x equal to 1. So there's a discontinuity at x equal to 1. How do you find the 0? Well, the 0 is when the numerator equal to 0. But there's a catch. Be very careful. Now watch this. This one's a bit special. If you factorize it, which is a difference of 2 squares, you will see that one of the 0 will cancel with the denominator. So that doesn't contribute to the 0 because it cancels. So the only 0, you meant to have 2 0, however, it's a discontinuity, is not counted as 0. So there's only one 0. That's a 0. That's a discontinuities. Discontinuities. All right, any questions? So it's pretty straightforward. Again, there will be various different questions you see in the textbook. Okay, let's move on to the next question. Now notice that we're going to draw this graph. Oh, what would the graph look like? You will look exactly like this. Look, we have this discontinuity. There's a hole there. Because when you cancel, your graph is y equal to x plus 1, right? As you can see. But because of the discontinuity, you have a hole there. So it's different from the asymptote we see when we have this, there's the asymptote. And if you go to university, these discontinuities has a name. This is called removable discontinuity. Not in the syllabus, that's called essential discontinuity. What does it mean? That can be fixed, right? It's just like unless there's a hole, just fill it in with the soil, right? You can't fill soil with that one. You just never fill it, just go to infinity, right? So there's a different type, right? Because that got cancelled. So that's a hole. Because essentially what you're drawing, you draw this graph with a hole there. So in this case, we can factor the top and bottom. The factors will cancel everywhere except at the common zero. So it cancels everywhere except, so when you write this, you have to write not equal to 1, right? Because otherwise when people see that, oh, it's the whole line. No, it's not the whole line. There's a 1 point removed, x equal to 1. You have to write that. It's like when you sell a product in the supermarket, make sure you include terms and conditions. Does that contain nuts? Does it contain peanuts? Write it down. You may contain traces of peanuts, whatever you call it. Okay, next one. Find the domain range of the curve. What's the domain? Anyone? No? Anybody? No? Matilda, what's the domain? Have a try. Have a guess. Have a look at it. What's the domain? No, please, I want the answer. I don't not seriously. Seriously. All right, ask someone else. Sonia. Domain. Oh my God, seriously. Look at it. The answers is screaming at you. Domain of this graph. No? Irene. Yep. That's all you have to say. Thank you. All right, move on. What's the range? Matilda, one more try. Range. Seriously. No. That's y now. So not talk about x. Except what? Look. No, not y equal to 1. Look. 2. Excellent. Thank you. All real y. Y not equal to 2. Thank you. All right, can start the exercise today. Thank you. Tomorrow we'll do more boring stuff, but okay. Thank you. All right. Good. Bye.